This study is written by myself, Angelo Rey Di Del Mundo, Mark Jacob Villaraya, and Dr. Jennifer C. De la Cruz. This study was conducted with the intent of contributing to telehealth services. With the prominence and fatal symptoms of various respiratory diseases, we propose the implementation of heat map analysis for a non-invasive respiration rate monitoring system that can operate effectively in a remote setting.
Telehealth or telemedicine enables remote healthcare in the comfort of homes using video conferences as a medium between the patient and the medical professional. It is also critical for rural areas or any other location far from clinical facilities. To this day, it remains relevant due to its accessibility and convenience. Chronic illnesses, such as chronic respiratory diseases such as COPD, affects over 380 million people globally. Over 3 million lives are cut short due to its silent and non-communicable nature, making it the world's fourth leading cause of death. Other respiratory diseases such as asthma, pneumonia, and even sleep apnea requires consistent monitoring. There are studies regarding derivation of respiration rate, such as by De La Cruz et al., where they use pulse oximetry to derive respiration rate from the heart rate. The signal processing techniques they use, such as the fast Fourier transform and Simlet wavelet transform, were used to estimate the heart rate and respiration rate. It is also worth to mention that there has been little to no mention of studies with regards of using MLX, as they have strictly limited options to more expensive and high-end models. Virtual consultations are not enough for effective respiration, health checkups, and patient assessment, since vital signs assessment and physical examination are used with medical tools to accurately assess patient health, wherein current telehealth services lack. Other high-end monitoring devices are usually used in hospitals or other specialized clinics. The main purpose of this research is to develop a vision-based respiratory rate monitoring system using a thermal camera for added temperature reading. Specific objectives include the following: device calibration and determination of the optimum location of the thermal camera in the monitoring setup, to observe the changes in temperature waveform as the patient breathes in and out and collect temperature data. And lastly, extract and derive respiration rate from the collected temperature signal data. The significance of our study is that it utilizes more affordable thermal camera, which is the MLX 9640, and cloud computing to showcase certain parameters and results remotely. It provides a real-time and non-invasive solution for monitoring respiratory health and addressing the lack of physical assessment tools in the telehealth system or services. Also, as respiratory death-related incidents continue to rise, primarily the COPD, early and accurate detection of respiratory-related diseases lessens the chance of complication, reducing the financial burden on healthcare services. For our delimitations, this study will mainly focus on creating ASP32-based infrared camera. The results will be compared to conventional approach of determining respiration rate by manual counting through the rise and fall of the chest or abdomen. The RMSE score and percentage difference will be determined for the accuracy of our proposed system. The study is limited to providing quantitative data on respiratory rate through thermal imaging. Other physiological parameters such as blood pressure and acidity levels would not be included.
This slide represents the conceptual framework that will be explained in greater detail in the subsequent slides. This is the flowchart that illustrates the comprehensive methodology employed for our data acquisition. Let us concentrate on this particular section for the time being. The MLX 9640 camera has a resolution of 32 pixels in width and 24 pixels in height, with a total of 768 pixels. With this information and utilizing the official GitHub repository for the thermal camera, we were able to convert each pixel into its corresponding temperature value based on their individual intensity levels. Using Python's OpenCV, we can reshape these values into a heat map. However, due to the aforementioned resolution, the camera's initial heatmap captures are too small and not ideal for determining our region of interest, which in this case is the nasal region. We have decided to resize them to a width of 170 by 205 pixels, giving us a clearer visualization of where the nasal region is located. A total of 1,690 thermal captures of similar size was used as our dataset for the nasal detecting YOLO V8 model, all of which were manually annotated using RoboFlow. Let's now focus on the middle part of the flowchart. The key factor in distinguishing whether a patient is inhaling or exhaling lies in the pixel intensity around the nasal region. As you can see on the left side, darker pixels represent colder temperatures, which suggests that the patient is inhaling cold air. On contrast, on the right side, brighter pixels indicate warmer temperatures, signaling that the patient is now exhaling the warmer air from their lungs back into the environment. The resulting confusion matrix of the YOLO V8 model looks like this. The performance metrics are this. Overall, it had decreasing losses and increasing performance metrics, with an overall trend suggesting successful training. Using these bounding boxes, it now becomes possible to identify specifically which amongst these 768 pixels refer to the patient's nasal region. However, it's important to note that our dataset utilized an enlarged heat map with dimensions of 170 by 205 resolution. In total, it has 34,850 pixels. To adhere to the parameters outlined by MLX 9640, we scaled down the bounding boxes relative to the original 768 pixel resolution. We applied the scaling factors on the right, and we were able to accurately determine the coordinates from the upper left and lower right corners of the bounding boxes corresponding to the true heat map resolution of our thermal camera. So these are examples of the cropped images of the nasal region relative to the 32 by 24 resolution of MLX 9640. As the system operates, it continuously captures heat map images of the nasal region. Each has distinct arrays representing the individual temperatures of their corresponding pixels. The size of these arrays varies based on the distance of the nose from the camera and the overall patient's size of the patient's nose. Whenever a detection occurs, we calculate the average of these temperatures and store them in a separate array. This array serves solely as a storage unit for future calculations. After 65 detections, the system invokes our custom respiration rate calculation function along with Python's pop function. The pop function ensures that the array maintains a maximum of 65 elements by removing the oldest entry. This allows the array to accommodate the latest average temperature readings of the nasal region while preserving efficiency. We chose a minimum of 65 detections before calculating the respiration rate for the following reasons. A sufficient amount of signal length is necessary to perform an effective fast Fourier transform analysis, and with 65 detections, temperature fluctuations are adequately captured. And with this threshold, we achieved an optimal trade-off balance between real-time responsiveness and signal reliability. We now move to the final section of the flowchart. Here is an example of the acquired raw temperature signals over a 2-minute period. Each data point here signifies a nasal detection. The Butterworth bandpass filter cutoff frequencies were selected based on the normal adult respiratory rate of 12 to 20 breaths per minute, corresponding to 0.2 Hz to 0.33 Hz. However, to account for irregular or faster breathing patterns, we opted to extending to 22 bpm or 0.367 Hz to ensure that respiratory-related signals are captured while filtering out noise, enabling accurate analysis of temperature variations associated with respiration. This is the resulting output after applying the bandpass filter. The next step now is involving the performance of the fast Fourier transform analysis to convert the time signal into a frequency domain. We applied a sliding window approach with a window size of 30 seconds and a step size of 10 seconds. This means that FFT analysis was performed on every 30-second segment of data. Afterwards, we shift for another 10 seconds before repeating the analysis. This process continues until the end of the 2-minute acquisition period of the data analysis. Here are the resulting frequency magnitudes after signal filtering. The peak frequencies here, within the bandpass range, corresponds to the respiratory rate in terms of Hertz. To convert this into BPM, we multiply these peak frequencies by 60 in order to get the respiration rate. And then finally here, we can see the respiration rate derived from the peak frequencies, providing us a means of monitoring a patient's breathing patterns over time.
Here is our prototype. We provided two indicators, visual and audio indicators. First is the LED, wherein the red LED will lit up once 65 nasal detections are done, and the green LED will lit up for every nasal detection together with a buzzing sound for the audio cue. And here is the MLX 9640 sensor or the thermal sensor. And here is the LCD display wherein it displays the raw temperature and the respiration rate. Here is the result of our data testing, in which there are total number of 10 trials wherein each trial consists of 2 minutes. As you can see, the lowest percent difference that we achieve is around 0.21%.
Significant deviations were observed in trials 1, 2, and 9 due to factors such as erratic patient movement, variability in breathing patterns, environmental noise, and the general hardware limitations of the MLX 9640 thermal camera. Despite these challenges, however, the proposed thermal system achieved an RMSE score of 1.651 when compared to the conventional method of manually counting the rise and fall of a person's chest. In conclusion, we successfully met the stated objectives of observing the temperature fluctuations in the nasal region, extracting raw temperature signals to derive respiration patterns, and providing visual and audio cues to effectively communicate system data to the user. The overall testing phase achieved an RMSE score of 1.651, with one testing showing a difference as low as 0.21% compared to manual counting. We recommend incorporating an industry-grade medical device for respiratory monitoring as a comparison tool, expanding the sample size to include a wider range of age groups, exploring alternative signal filtering techniques, and applying the same image analysis methodology with a more advanced thermal camera, inexpensive of course for a more expensive model. That is all, and thank you for listening to our presentation.